What secrets lurk within the heart of the universe, guarded by the most colossal and enigmatic forces known to science? In a single, boundless journey through the cosmos, our documentary seeks to unravel the mysteries of the stars. From the behemoths dwarfing our sun to the remnants of cosmic cataclysms. We begin with the titans among stars, those astronomical marvels whose sheer size and power eclipse our solar system's very heart, propelling us to question the very nature of size and existence. How do these giants come to be, and what fate awaits them as they burn through the eons? Our gaze then shifts to our own star, the Sun, observed tirelessly by NASA's Solar Dynamics Observatory over a decade. This sentinel in space reveals the Sun's fiery temper and dynamic nature, challenging our understanding of the star that sustains life on Earth. What have we learned from a decade of unwavering observation, and how does this knowledge shape our relationship with the cosmos? And finally, we delve into the realm of neutron stars, the densest and most mysterious objects in the universe. Born from the cataclysmic death throes of massive stars, these remnants challenge our comprehension of matter and gravity. As we explore the aftermath of their violent collisions, we're left to ponder. What do these cosmic beacons tell us about the universe's fundamental laws and the possibilities of extreme physics? Join us on a journey that spans the vastness of space and time, from the incomprehensibly large to the infinitely dense, each discovery a chapter in the ongoing story of our universe. Among the mysteries of the cosmos, the true titans of the universe are the stars. Imagine a star of unfathomable size and power, so huge that it eclipses our sun, making it a speck in comparison. Today we turn our eyes upward, not just to admire the beauty of stars, but to go in search of colossal, extraordinary, the largest stars known to science. Our sun, the heart of the solar system, is just a speck of light against the backdrop of these giants. Stars so huge that they can encompass not only Earth or the inner planets, but extend beyond the orbit of Mars, and in some cases, even further. But what makes a star big? Is it mass, volume, or perhaps their effect on the surrounding cosmos? Our quest doesn't end with size alone. We'll look into the hearts of these giants, exploring the nuclear furnaces that fuel their glow and forces that may one day bring about their spectacular demise. Are you ready to explore the limits of the known universe and look into the heart of these space giants? Let us embark on a space journey that begins right here on Earth. Our planet, though conveniently just a speck in the grand scale of the universe, will be the starting point on the timeline. Now let's move on to Jupiter, the colossus of our solar system. It's not just another planet, it's a completely different beast. Jupiter is 11 times larger than Earth and 300 times more massive. Our first step toward understanding the vastness of the cosmos. Jupiter serves as a cosmic bridge from rocky worlds like ours to the gaseous worlds. It's composed mostly of hydrogen and helium, the same components that make up stars. It's not just a larger version of Earth, it's a fundamental shift in composition and characteristics, a formation that is beginning to take on the characteristics of the stars that light up our night sky. In cosmic science, mass and volume are key to understanding the difference between such giants and stars. Mass tells us about the gravitational power of an object and its ability to fuse elements in its core, determining its life cycle. Volume, on the other hand, gives us an idea of size and how much space this body occupies in outer space. These differences are fundamental to understanding the true nature of stars. It just so happens that the smallest mass of a gas cloud that can collapse to form some sort of star is about 1 Jupiter mass. It is at this mass threshold that we encounter a fascinating class of objects known as sub-brown dwarfs. These mysterious entities, often called rogue planets, are on the boundary between the largest planets and the smallest stars. They have the same composition of hydrogen and helium as Jupiter, but on a larger scale, at times leaning toward the deuterium burning mass that is the threshold for brown dwarf classification. However, sub-brown dwarfs lack the mass required for sustained hydrogen fusion, the hallmark of a true star, putting them at a cosmic impasse. With masses below the threshold required for thermonuclear fusion, they occupy a unique niche in the cosmic continuum for understanding the formation and evolution of celestial bodies. As we go deeper into space, we encounter the already mentioned brown dwarfs. These failed stars are interesting because they cannot sustain hydrogen fusion in their cores, a process that defines true stars. With masses ranging from 13 to 80 times that of Jupiter, they're much heavier than any planet, but they still lack the mass to ignite the nuclear fire that powers stars like our Sun. Because of this, they're in a cosmic limbo, glowing dimly from the heat of their formation, but never achieving the full nuclear fission that characterizes full stellar life. Moving beyond the realm of substellar objects, we enter the realm of red dwarfs, the most common and long-lived stars in the universe. These tiny stars mark the threshold beyond which stable hydrogen fusion begins, making them the main sequence stars that populate our galaxy in vast numbers. Red dwarfs are the founders of the cosmos, with lifespans of trillions of years, far surpassing the longevity of stars such as our Sun. Their longevity and abundance make them prime candidates for the search for extraterrestrial life, as their stable and long-lived nature gives enough time for planets in their habitable zone to potentially develop complex life forms. It is also interesting that these are the only main sequence stars that do not grow in volume when they die, but simply go out towards the end. Incidentally, the closest red dwarf to us, Barnard's star, is 5.96 light-years away and is the fourth closest star to the Sun after the 3 components of the Alpha Centauri system. Its stellar mass is about 16% of the Sun's mass, and its diameter only about 1/5 of the Sun. Despite its proximity, the star is invisible to the naked eye. As we move away from the dim glow of red dwarfs, we reach the familiar warmth of our own Sun. The Sun, a main sequence star, is the baseline for understanding stellar magnitude. Its mass, brightness, and lifespan are the yardsticks by which we measure the true giants of the cosmos. With a temperature twice that of Barnard's star, the Sun shines several hundred times brighter than it. Moving on, we encounter Sirius, the brightest star in our night sky. Twice as massive as our Sun, its brilliance depends not only on proximity but also on its own luminosity. It shines 25 times brighter than the Sun. At this stage, relatively small changes in mass correspond to an unimaginable increase in the brightness of main sequence stars. However, by burning its material so vigorously, the star shortens its lifetime by a factor of 4. The journey doesn't end there. Beta Centauri, a binary system, showcases stars whose masses are 10 times that of the Sun and whose surfaces blaze at unimaginable temperatures, 2.5 times that of Sirius. Such incandescence causes them to shine 20,000 times brighter than our Sun. However, possessing a rather impressive mass, scientists have diagnosed its lifespan at only 20 million years. Our journey through space brings us to the threshold of giants and hypergiants, stars that challenge the size limits of the stellar world. Hypergiants, larger than supergiants and giants, are rare stars that shine extremely brightly. By studying their enormous size, radiated power, and intriguing aspects of their measurements, we're discovering new information about the life cycles of the most massive stars in the cosmos. In the world of giants, UY Scuti, Stephenson 218, and WOH G64 are monumental figures, each embodying extreme aspects of stellar evolution. UY Scuti, a red hypergiant in the constellation Scutum, is known for its huge radius, making it one of the largest observable stars. Back in 1860, German astronomers from the Bonn Observatory first cataloged UY Scuti. A few years ago, this star gained lots of popularity as the largest star known to us. However, recent recalculation of distances has pushed it back down the list. The star is located near the center of the Milky Way, about 5,900 light-years from Earth. UY Scuti is nearly 800 times the size of our Sun. A star of this type loses most of its mass due to fast-moving stellar winds that take some of its materials with them. However, for all that, while remaining quite impressive, our candidate now does not even make it into the top 80 largest stars known to us. Stephenson 218, another red supergiant, thought to be the largest just a couple of years ago. The star's radius is estimated by some sources to be 2,150 solar radii. To make you realize the size, if you put the star in our solar system, Saturn's orbit would girdle its radius. And if you wanted to orbit it at the speed of light, one lap would take you an astonishing 9 hours. For example, the same trip around the Sun would only take 14.5 seconds. However, its luminosity is well above the Humphreys-Davidson limit, which we'll discuss later, and perhaps for this reason, it's not a member of the Stephenson 2 cluster, which makes its location, as in the case of UY Scuti, closer, and consequently its size much smaller. So who actually takes first place, you ask? As of today, according to the list of the largest known stars, the leader is WOH G64. It has a radius of 1,540 solar radii. This means that if the star were at the center of our system, it would swallow the orbits of Mercury, Venus, Earth, Mars, and even Jupiter. This radius even fits within the stellar evolution limit, which we'll discuss next. Across the vastness of the universe, astronomers use state-of-the-art techniques to measure giant stars. One such method involves the use of spectroscopy, an instrument that analyzes the light emitted by stars. By decomposing starlight into its constituent colors, spectroscopy can determine the chemical composition, temperature, density, and relative motion of these celestial giants. This technique has played a crucial role in the study of WOH G64, revealing its enormous size and the intricate details of its surrounding dust envelope. Another innovative approach is interferometry, which combines the capabilities of multiple telescopes to model a larger aperture. This method greatly improves resolution, allowing astronomers to distinguish surface features and angular sizes of distant stars. The use of interferometry has led to breakthroughs in understanding stars such as UY Scuti and Stephenson 218, allowing us to understand their physical size and surrounding circumstellar material. Measuring the sizes of stars is difficult, primarily because of their vast distance and the complex structure of their outer layers. Such stars as WOH G64 are not only distant, but also shrouded in dense dust clouds, making direct size measurements difficult. The variability of these stars adds yet another layer of complexity, as their outer envelopes can expand and contract over time, changing their apparent size. In addition, the brightness and luminosity of these stars can lead to error in observations. The intense light can obscure the true edge of the star, making it difficult to determine where the star ends and the surrounding nebula begins. This ambiguity was a significant factor in the initial reassessment of the size of a large number of stars. The path to understanding these celestial giants also forces us to confront the stellar evolution limits in the Milky Way, often referred to as about 1,500 solar radii. This limit is related to theoretical limits on how large stars in our galaxy can become. The main factor determining a star's size and evolution is its mass. More massive stars have stronger gravitational forces that compress the core, resulting in higher temperatures and pressures. In the core, hydrogen atoms fuse to form helium, releasing energy in the process. This energy counteracts the gravitational force to collapse the star, keeping it stable. The limit of 1,500 solar radii is often associated with the Humphreys-Davidson limit, named after astronomers Roberta M. Humphreys and Chris Davidson. It denotes the region of the critical threshold on the diagram beyond which the luminosity of a star becomes so extreme that it can lead to its destabilization. In our case, it was an important milestone in the reassessment of the size of Stephenson 218. The initial classification of Stephenson 218 as one of the largest stars was called into question by its luminosity, which exceeded the Humphreys-Davidson limit. This paradox suggested that either our understanding of stellar physics needed refinement, or that the star's size was overestimated because of the difficulty of measuring such distant objects. It's also interesting that stars approaching or exceeding this limit experience significant mass loss due to a powerful stellar wind. The intense radiation pressure created by their extreme luminosity stimulates mass loss, forcing the star to shed its outer layers. Eventually, stars that have exceeded the limit of stellar evolution face an unsafe fate. When their core can no longer withstand the gravitational pressure, it rapidly collapses, leading to a cataclysmic supernova explosion. These explosions are some of the most energetic events in the universe. They scatter heavy elements into space, often leave behind compact remnants, such as neutron stars or black holes. Exploring these limits highlights the delicate balance between mass, luminosity, and stability that allows these colossal stars to exist. It provides invaluable insight into the life cycles of the universe's most massive inhabitants. In the cosmic scene, size and mass often go hand in hand, but there are intriguing exceptions to this observation. It's natural to assume that the largest stars should also be the most massive, but the universe has a knack for refuting our expectations. This paradox is perfectly illustrated when we delve into the realm of colossal stars such as BAT 99-98. BAT 9998, a supergiant star, located in the large Magellanic Cloud constellation Doradus, boasts a colossal mass far beyond what we might expect based on its radius alone. With a mass of 226 solar masses, BAT 9998 is one of the most massive discovered to date, if not the most record-breaking. Despite the exceptional mass, the star is not remarkable for its large size. Its radius is 37.5 times that of the Sun, which corresponds to the size of a polar star, a white supergiant with a mass of 5.4 solar masses. However, as expected, both BAT 9998 and Polaris are not among the largest known stars. Residing in the Tarantula Nebula, a huge stellar nursery, it's among the most massive and brightest stars. BAT 9998 is rivaled by a close fellow Wolf-Rayet star, R136A1, located in the R136 cluster near the center of the Tarantula Nebula. As for the fate of such a star, BAT 9998, like many similar stars, is a candidate for supernova or hypernova. The exact outcome depends, of course, on the amount of mass lost. A supergiant may produce a gamma ray burst and leave behind a neutron star or black hole, or it may not produce a visible supernova at all. In general, the life cycle of stars is quite intriguing. Stars begin their lives in the cold, dark corners of the universe in vast molecular clouds. These clouds, rich in gas and dust, serve as cosmic nurseries where gravity pulls the material together to form the heart of a new star. As the nascent star's core becomes denser and hotter, a dramatic transformation takes place. Nuclear fusion begins, turning hydrogen into helium and releasing a torrent of energy that lights up the cosmos. This fusion process is the star's powerhouse, the engine of its luminosity and heat. For stars like our Sun, this harmonious balance between gravitational forces and nuclear energy keeps them going for billions of years. However, this stage is only the beginning of their cosmic journey. As stars age, their fuel begins to run out. The Sun, for example, will undergo a dramatic transformation, becoming a red giant. This expansion is a paradox. Even as a star sheds its outer layers into space, it increases in size, becoming a huge, glowing ball of light that can engulf the inner planets of the solar system. But the life cycle of a star is not only a story of growth, it's also a story of loss. As the red giant phase fades, stars like our Sun shed those outer shells, forming ethereal structures known as planetary nebulae. The remaining core, stripped of its former glory, becomes a white dwarf, a dense, dim remnant of the star's heart. For more massive stars, the end is even more spectacular. Their demise comes in the form of a supernova, an explosion of unfathomable scale and beauty that eclipses entire galaxies for a brief moment. What remains may be a neutron star, or, if massive enough, a black hole. In this grand cosmic cycle, stars are not just points of light in the night sky. They are the forges of the universe, the creators of the elements that make up the world around us and within us. From their fiery birth to their spectacular death, stars are the architects of the cosmos, shaping the universe in their own image, one stellar life cycle at a time. Giant stars of enormous luminosity and size serve as cosmic beacons that illuminate the mysteries of the formation and evolution of the universe. By studying them, astronomers unravel the complex tangle of stellar life cycles, from the initial collapse of molecular clouds to the explosive finale of supernovae. The theoretical limits on the size of stars are still subjects of fierce debate among astrophysicists. However, in the realm of cosmic records, the title of largest star remains a dynamic prize. Discoveries and improved observational techniques are constantly revising the upper echelons of the stellar sizes. This fluid nature of space records once again emphasizes the vastness of the universe and the constant search for knowledge that drives our exploration of the cosmos. So, let's stay inquisitive as we eagerly await the discoveries that our universe holds. In the vastness of our system lurks a considerable mystery, a source of energy and life, our Sun. For a decade, the Space Guardian, NASA's Solar Dynamics Observatory, has been our unblinking eye on this fiery giant. This mission, launched into space February 11, 2010, set out on an odyssey not just to observe, but to unravel the mysteries of our nearest star. Imagine a world where a single second reveals a story millions of years old, where plumes of fire burst from the surface of the Sun, larger than the Earth itself. It's a world that explores SDO, a world where every 3/4 of a second a new image is captured, each one a piece of the puzzle in understanding the Sun's impact on our solar system. As we venture through a decade of solar observations, we're immersed in a realm where colossal waves ripple across the Sun's surface, where plasma eruptions challenge our understanding of physics, and where the solar cycle resonates throughout the solar system. This is not just a journey of a satellite and a star. It is a story of discovery, the challenges faced, and overcoming them. Our journey with the Solar Dynamics Observatory begins with a momentous event: launch. February 11, 2010. Amidst the roar of the engines and the fiery takeoff of the Atlas V rocket, SDO begins its mission to explore the mysteries of the Sun. This launch marked not only the beginning of the mission, but also the beginning of a new era in solar observations. Once in space, SDO moved into geostationary orbit, positioned to have an unobstructed view of the Sun. Its main goal? To understand the Sun's influence on Earth and the solar system by studying the solar atmosphere in unprecedented detail. Central to this mission is a suite of sophisticated instruments aboard SDO, each designed to study different aspects of the Sun's behavior. Prominent among them is the Atmospheric Imaging Assembly. This remarkable instrument takes images of the solar atmosphere at different wavelengths, each revealing different features of the Sun. The capabilities of the AIA are truly revolutionary. It observes the Sun in 10 different wavelengths, each tuned to a specific temperature of solar material. This allows scientists to see the Sun's surface and atmosphere in a spectrum of colors, with each color revealing unique phenomena. AIA's observations have been instrumental in advancing our understanding of solar dynamics, from cooler and darker sunspots to blazing hot coronal loops. Over the past decade, it's tirelessly observed the Sun, taking more than 425 million high-resolution images, each image contributing to a continuous stream of data, painting a vivid portrait of the Sun's dynamic behavior. Why do we study the Sun so diligently? The answer lies in the Sun's profound influence on our system. It is the heart of our cosmic environment, controlling processes from polar lights on Earth to weather patterns on other planets. Understanding the sun means understanding the fundamental processes that govern our corner of the universe. Through the eyes of the AIA, we witness the story of the sun unfold in real time. Ejections of solar material, twisting magnetic fields, and the intricate dance of solar flares have all been captured in stunning detail. The AIA didn't just open a window into the sun's activity, it paved the way to understanding the complex interactions that drive solar weather. This decade-long observation has revealed the dynamic nature of the sun in unprecedented detail. From the ebb and flow of solar flares to the mysterious 11-year solar cycle, SDO has provided insight into phenomena that was once mere speculation. The mission has witnessed previously unfathomable solar events. Across the vast expanse of space, the Solar Dynamics Observatory plays the role of a vigilant observer, capturing every nuance of the sun with unprecedented precision. Over its decade-long operation, SDO has amassed a stunning collection of more than 425 million high-resolution images, creating a continuous image of the sun's ever-changing face. Imagine a world in which every fraction of a second reveals a new aspect of our star. SDO operates in such a mode, acquiring images of the sun every 0.75 seconds. This relentless pace of observation allows us to see the dynamic nature of the sun in real time, capturing processes and changes that were once beyond our view. SDO's ability to observe the sun at different wavelengths has opened up new possibilities for understanding our star. Each wavelength reveals a unique layer of the sun's atmosphere, from its turbulent surface to the outer limits of its corona. This multi-wavelength approach allows us to see the sun in all its manifestations. Among the wavelengths that SDO observes, one that stands out is the extreme ultraviolet wavelength of 17.1 nanometers. This particular wavelength gives us a unique view of the solar corona, the outermost part of its atmosphere. The corona is a hotbed of solar activity, where temperatures reach millions of degrees, and where the mysteries of solar phenomena such as coronal mass ejections and solar flares lie. Through the SDO prism, the corona is no longer a dark region, but a bright, dynamic environment. We see coronal loops, giant arcs of plasma driven by the sun's magnetic field, and witness eruptions that send waves of solar material into space. These observations are not just visually stunning, they are key in helping us understand how the sun affects space weather and, in turn, our own planet. As we continue to explore the sun with SDO, every image and observation at every wavelength adds to our understanding of our star's enigmatic corona, revealing a dynamic and complex celestial body like never before. By embarking on a quest to decipher the 11-year solar cycle, the Solar Dynamics Observatory has been at the forefront of solar science. This cycle, a rhythm that's puzzled astronomers for years, is characterized by periodic changes in the sun's activity, including the frequency of sunspots, solar flares, and coronal mass ejections. SDO's decade-long observations cover nearly a full solar cycle, offering a front-row view of the sun's changing dynamics. During periods of solar maximum, the sun is a swarm of activity, teeming with sunspots and erupting with intense solar flares. Conversely, during solar minimum, the sun enters a quieter phase with fewer sunspots and less surface activity. Throughout its mission, SDO has witnessed and meticulously recorded many solar events. Incredible eruptions of plasma known as coronal mass ejections have been captured in detail, revealing the enormous energy released as these events unfold. Solar flares and intense bursts of radiation have been observed in different wavelength ranges, providing insight into the mechanisms that trigger these explosive events. In addition to this spectacle, SDO has also observed rare and mesmerizing passages of planets along the Sun's surface. These events, while exciting in their own right, serve a more important purpose in solar science. They offer unique opportunities to study the Sun's atmosphere and its interactions with celestial bodies, further expanding our understanding of solar dynamics. In space exploration, challenges are as inevitable as they are varied. NASA's Solar Dynamics Observatory has faced its fair share of obstacles, each of which has tested the mission's resilience and ingenuity. From Earth shadows and lunar eclipses to technical obstacles, such as the Atmospheric Imaging Assembly instrument problem in 2016, SDO's path has been thorny and winding. One of the persistent problems SDO faces is eclipses caused by the Earth and Moon. These celestial landmarks, although a natural part of the orbital path, temporarily limit SDO's ability to observe the Sun. Earth eclipses occurring on equinoxes cast a shadow over the observatory, resulting in short periods of darkness and interrupted data transmission. Similarly, lunar transits, although rarer, momentarily block SDO's view of the Sun, creating a unique but challenging scenario for solar observing. In 2016, SDO faced a major challenge when its key instrument, the Atmospheric Imaging Assembly, encountered technical difficulties. This failure jeopardized one of the mission's most important data streams. The AIA, responsible for high-resolution imaging of the solar atmosphere, is integral to understanding the Sun's dynamic behavior. The problem with AIA was complex and revolved around the problem of detecting and analyzing invisible coronal mass ejections. These CMEs, which occur at high altitudes in the solar corona and regions with weaker magnetic fields, are notoriously difficult to observe. Unlike typical CMEs, which appear as visible dimmings or brightenings on the Sun, hidden CMEs can often be detected only with special instruments like a chronograph. Solving the AIA problem required a coordinated effort between engineers and scientists. The team applied new techniques to visualize the remote sensing data acquired by the AIA by comparing different images, current images of the Sun with images taken 12 hours earlier. The team was able to capture slow changes in the lower part of the corona. This method revealed subtle, previously overlooked changes in the Sun's magnetic fields and plasma loops. Advanced image processing techniques, including wavelet packet equalization and multi-scale Gaussian normalization, were applied to improve the visibility of these subtle changes. These techniques allowed the team to detect dimmings and brightenings in the Sun's disk associated with hidden CMEs, which was a breakthrough in solar observation. Successfully addressing these changes not only allowed the mission to continue, but also enriched our understanding of what it takes to sustain a long-term space observatory. As we delve deeper into the implications of the Solar Dynamics Observatory findings, we discover the Sun's profound influence not only on Earth, but also on the broader expanse of space. Decades of SDO observations have greatly advanced our understanding of space weather and its many implications for our planet and beyond. Space weather, the term for the energetic activity of the Sun, includes phenomena like solar flares, coronal mass ejections, and solar energetic particles. These events, born from the Sun's dynamic surface and atmosphere, can propagate through space, affecting both planets and spacecraft. When it comes to Earth, The effects of space weather are both interesting and far-reaching. The interaction of solar wind and coronal mass ejections with Earth's magnetosphere can lead to spectacular auroras, commonly known as the northern and southern lights. However, these interactions can also have more devastating consequences, such as disruptions to satellites, communication systems, and even power grids. The SDO findings have played a significant role in enhancing our ability to predict space weather events. By understanding the mechanisms that cause solar eruptions and their trajectories, scientists can better predict when and how these events might affect Earth. Such prediction is critical to preparing and protecting our technological infrastructure in space and on the ground. Beyond Earth, the implications of SDO research extend throughout the solar system. Understanding space weather is vital to the safety of astronauts in space and to the planning and execution of interplanetary missions. As we venture deeper into space, whether the Moon, Mars, or beyond, knowledge of the Sun's behavior becomes increasingly important. To summarize, the implications of a decade of SDO observations are profound and far-reaching. This mission's not only deepened our understanding of space weather and its impact on Earth, but it has laid the groundwork for safer space exploration for coming decades. As we look into the future of solar observations, the horizon is full of hope and potential. The current era of solar exploration is marked by groundbreaking missions such as the Parker Solar Probe and Solar Orbiter. The Parker Solar Probe, launched in 2018, has already come closer to the Sun than any spacecraft ever before, and will eventually dive into the corona to tell us about its mysteries. The Solar Orbiter, the product of a collaboration between ESA and NASA, launched in 2020, and it's equipped to provide a comprehensive view of the Sun's poles and its outer atmosphere, previously unexplored regions. These missions are equipped with state-of-the-art instruments designed to study the Sun in new ways. The Parker Solar Probe's journey through the solar corona promises insight into fundamental processes that govern the solar wind and solar energetic particles. The Solar Orbiter's unique orbit and extensive suite of instruments will provide a holistic view of the Sun's atmosphere, magnetic field, and solar wind. Looking ahead, the future of solar observation has brilliant potential. The opportunities for new discoveries are as vast as the Sun itself. We can unlock the secrets of the Sun's magnetic field dynamics, leading to a better understanding of solar flares and coronal mass ejections. Studying the Sun's inner workings could reveal more about the workings of its 11-year solar cycle. As we continue to observe and study the Sun, we stand on the threshold of a new era in solar science that promises to illuminate the darkest corners of our understanding of the star that sustains life here on Earth. Today we're going to talk about one of the many interesting stories lying in the depths of space. It is a story not about luminous stars or spiral galaxies, but about the most mysterious and dense objects in the universe: neutron stars. Our story begins with a violent and colorful ending, a supernova explosion. In this spectacular celestial fireworks display, the death of a massive star gives rise to something extraordinary. From the heart of this cosmic eruption, a neutron star is born. The stellar remnant is so dense that just a teaspoon of its material weighs as much as a mountain. But what happens when these stellar remnants, these neutron stars, are not alone? What secrets do they reveal when they collide in a catastrophic confrontation between gravity and light? Today we'll witness extreme physics in action, explore the rippling fabric of space-time, and hear the whisper of the universe through gravitational waves. In the vast cosmos, the life of a star is a story of transformation and energy. Our story begins with a colossal star, much more massive than our Sun. At the core of this giant, a fierce battle rages between gravity and nuclear forces. This star, like all stars, is a nuclear furnace. In its core, hydrogen atoms fuse to form helium, releasing enormous amounts of energy. This process of thermonuclear fusion is the basis of a star's life, the delicate balance that sustains it for millions, even billions of years. But nothing lasts forever. When a star exhausts its hydrogen fuel, it enters the next phase of its life cycle. The core contracts under the relentless pull of gravity, heating up further and igniting helium in a process called helium burning. This stage is brief compared to the hydrogen burning phase. Now the star expands to become a red supergiant, a colossal object in space. Then comes the final act, a supernova. When a massive star runs out of nuclear fuel, the process of thermonuclear fusion in its core stops. Without the external pressure created by fusion, the core becomes unstable. In a decisive battle with its gravity, the star's core begins to collapse. The collapse of the core is rapid and catastrophic. In less than a second, the nucleus, which was once the size of the Earth, shrinks to a radius of about 10 miles. This collapse occurs because electrons and protons in the nucleus fuse to form neutrons and neutrinos due to the extreme pressure and temperature. The collapse of the outer layers of the star bounces off the incredibly dense core, causing a supernova explosion. This explosion ejects the outer layers of the star into space, creating a brilliant light show that outshines entire galaxies. The supernova is not just an ending, but an impressive beginning. From the heart of this cosmic explosion, a neutron star is born. It's a bizarre and exotic object, incredibly small compared to the star it once was, but incredibly dense. The star's matter is now mostly neutrons packed tightly together, with no space between them. The material of a neutron star the size of a sugar cube would weigh as much as a mountain on Earth. Conservation of angular momentum causes a newly formed neutron star to spin at phenomenal speeds. This, combined with an intense magnetic field, trillions of times stronger than Earth's, makes neutron stars some of the most extreme environments in the universe. In essence, the formation of a neutron star is a journey from the agony of a massive star to the birth of one of the most mysterious objects in the cosmos. So let's take a closer look at these cosmic bodies, because they're not just amazing astronomical objects. They're the key to unlocking some of the deepest mysteries of the universe. As we mentioned, neutron stars are among the densest objects in the universe, second only to black holes. Imagine, if you will, a mass greater than that of our Sun compressed into a sphere about 20 miles in diameter. The magnetic fields of neutron stars are just as extreme. They are trillions of times stronger than the Earth's magnetic field. These intense magnetic fields are responsible for some of the most dynamic phenomena observed in the universe, such as the emission of powerful beams of radiation. Inside the star itself is a realm of matter under conditions unattainable in any laboratory on Earth. The outer layer of crust of a neutron star consists of a lattice of nuclei immersed in a sea of electrons. Deeper in, the density increases, and the matter is thought to transform into a substance known as nuclear pasta. bizarre state in which protons and neutrons rearrange themselves into complex structures. This nuclear paste represents one of the strongest known materials in the universe, with a strength billions of times greater than steel. As we move toward the nucleus, the matter becomes even more mysterious. Theory suggests that it may be composed of free quarks or even weird matter. Strange matter is a hypothetical substance consisting of equal numbers of top and bottom quarks, as well as strange quarks potentially formed under the extreme conditions of a neutron star's core. To truly appreciate the scale and density of neutron stars, let's visualize them in comparison to objects with which we're more familiar. Compared to Earth, neutron stars are tiny in size but much more massive. Their gravity is so strong that if you dropped an object from just 1 meter above the surface of a neutron star, it would fall to the surface in a microsecond at thousands of miles per hour. Neutron stars, with their extreme density, powerful magnetic fields, and unique internal structure, are not just supernova remnants. They are cosmic laboratories that allow us to study physics under conditions otherwise impossible to achieve, and provide a glimpse into the fundamental structure of our universe. Pulsars, the so-called beacons of the galaxy, are in turn one of the most intriguing phenomena in the universe. Let's try to understand these mysterious objects. Pulsars are a special type of neutron stars characterized by rapid rotation. They are all the same remnants of massive stars that exploded with supernovae and turned into dense cores. The rotation of a pulsar can be incredibly fast. Some rotate hundreds of times per second. Pulsars, as they rotate, emit beams of electromagnetic radiation from their magnetic poles. Because of their strong magnetic fields, these beams are sharply focused, like a lighthouse beam. As the pulsar rotates, these rays sweep across the sky. If they are Earth-oriented, we see them as regular pulses of light or radio waves, hence the name pulsar. Pulsars are known for their remarkable regularity. The precision of their pulses can rival that of atomic clocks, making them valuable as cosmic timekeepers. This regular pulsation allows astronomers to study phenomena like gravitational waves and the interstellar medium, and even test the theory of relativity. Observatories such as Chandra X-ray Observatory and Very Large Array record the rhythmic pulses of pulsars. These observations help scientists understand extreme physical phenomena and stellar evolution. In the vastness of space, neutron stars are not always lone wanderers. Some exist in binary systems bound by gravity, creating a stellar duo of immense energy and complexity. In double systems, neutron stars have profound effects on each other and the surrounding celestial bodies. These interactions can lead to many stunning and complex astronomical phenomena. Their extreme gravitational attraction can lead to phenomena such as mass transfer, where material from one star is attracted to its companion. This process can dramatically alter the evolution of both stars, leading to explosive events and even the formation of black holes. When neutron stars and double systems orbit around each other, they create ripples in the fabric of space-time known as gravitational waves. These waves carry energy away from the system, causing the neutron stars to gradually move closer together. The detection of these gravitational waves has become a key technique for studying double neutron star systems and has provided direct evidence for the correctness of Einstein's general theory of relativity. Neutron stars can also affect any nearby planets or objects with their gravitational reach. Their intense magnetic fields and emitted radiation can radically alter the environment of these bodies. potentially destroying their atmospheres or irradiating their surfaces. The study of these effects provides insight into the survival of planets and objects in extreme environments. When neutron stars move through space, especially in double systems, they can interact with the interstellar medium, the gas and dust that fills the space between the stars. This interaction can lead to unique radiation signatures. It can even produce complex structures such as headshock waves when the material of the interstellar medium is compressed and heated by the neutron star's motion. The discovery of exoplanets orbiting neutron stars is a testament to the diversity of planetary systems. These planets, formed from supernova remnants, provide fascinating insights into the stability of planetary bodies and the diverse environments in which they can exist. Advanced computer simulations have become invaluable in the study of these systems. They allow scientists to model the complex gravitational interactions in double systems and the orbits of exoplanets around neutron stars. These models are key to understanding the stability and evolution of such systems, shedding light on phenomena that cannot be observed directly. These diverse interactions emphasize the dynamic nature of the neutron stars and double systems. They are not just the end product of stellar evolution, but active, influential players in the cosmic landscape. Now let's meet one of the most epic events in the universe, the Kilonova, a colossal explosion resulting from the collision of two neutron stars. This catastrophic event is not just cosmic fireworks. It is the crucible in which the universe forges some of its most precious elements. A Kilonova star occurs when two neutron stars orbiting each other eventually converge and collide. This collision is so powerful that it distorts the very fabric of space-time, emitting gravitational waves that vibrate through space. This collision also causes an explosion of energy that briefly outshines even the brightest galaxies. One of the most interesting aspects of the Kilonova is its role in the creation of heavy elements. During a collision, conditions are created for the rapid process of neutron capture, also known as R process. In this process, neutrons bombard atomic nuclei, creating heavier elements like gold, platinum, and uranium. These elements are then ejected into space by the force of the explosion, eventually becoming part of other stars, planets, and even life on Earth. Renditions of two neutron stars spiraling toward each other are not just stunning visualizations. They are based on complex astrophysical models. These models help scientists understand the dynamics of the collision, the energy released, and the fusion of heavy elements. The visuals convey the dramatic and violent nature of this event. Kilonova represents one of the most powerful and transformative events in the universe. Now let's delve deeper into the profound impact neutron stars have on our understanding of the structure of the universe. These celestial objects, dense remnants of supernovae, are not just astronomical curiosities. They're key players in extreme physics and multi-messenger astronomy. Neutron stars offer an unprecedented opportunity to study the physics of stars at the most extreme stages of their evolution. The collision of neutron stars, resulting in the emission of gravitational waves, provides new insights into the final stages of stellar evolution. As France Cordova, director of the National Science Foundation, observed, these observations, quote, transform our understanding of the universe with a fresh narrative about the physics of stars in their death throes, end quote. The detection made by the National Science Foundation supported Laser Interferometer Gravitational Wave Observatory, or LIGO, confirmed a major prediction of Albert Einstein's 1915 theory of general relativity. In 2017, a century later, scientists discovered gravitational waves emanating from a collision of two neutron stars, a groundbreaking moment in astrophysics. The event was significant because it confirmed Einstein's predictions and marked the beginning of a new era in gravitational wave astronomy. The simultaneous detection of gravitational and electromagnetic waves from neutron star collisions has ushered in the era of multi-channel astronomy. This dual approach allows scientists to hear the sound of the gravitational wave at the same time see the colors of light, offering a more complete understanding of cosmic events. It opens new possibilities for exploring the universe by combining gravitational wave data with electromagnetic observations for a holistic view of the astrophysical phenomena. Laura Catanati, a professor of physics at Georgia Tech and deputy spokesperson for the LIGO Scientific Collaboration, shared her views on this monumental discovery and emphasized, "We are learning new things about physics, about the universe, about the elements that we are made of, and no one has ever done this before." The future of neutron star research is illuminated by several ambitious missions and projects. These include state-of-the-art space telescopes and ground-based observatories designed to observe neutron stars at a variety of wavelengths, from radio to gamma rays. The increased sensitivity of gravitational wave detectors will allow for more precise studies of waveforms, leading to a better understanding of the properties and behavior of neutron stars. The upcoming missions are designed to further explore the structure and behavior of neutron stars. The goal of these missions is to answer fundamental questions about the state of matter under extreme conditions. The future of neutron star research has important implications for astrophysics and cosmology. Increased detection of gravitational waves will allow scientists to test and refine theoretical models, including Einstein's theories. This research will not only advance our understanding of neutron stars, but also address fundamental questions about the expansion of the universe and its underlying physics. Just as importantly, such research will provide a deeper understanding of the insides of neutron stars, the nature of their emissions, and their role in the cosmic landscape. Looking to the future, the study of neutron stars stands on the threshold of discoveries and advances. It promises not only to improve our understanding of the universe, but also to inspire new generations of scientists and astronomers to explore the uncharted depths of space.